Hello, this is Mrs. Henry, and these are notes for finding empirical formulas. Before we talk about empirical formula, I want to remind you that a chemical formula is a ratio of both atoms and moles. We are very used to understanding it as a ratio of atoms, but it is also a ratio of moles. So as a reminder, the formula for glucose is C6H12O6, and this means that the one mole of glucose has, or contains, might be a better word, 6 moles of carbon, 12 moles of hydrogen, and 6 moles of oxygen. So because a chemical formula is a ratio of moles as well as atoms, we can use this information to help us find chemical formulas. An empirical formula is different. It gives the simplest whole number ratio of the atoms or moles of the elements in a compound. So for example, we know that the glucose chemical formula is C6H12O6. The empirical formula, the lowest whole number ratio for glucose, would be CH2O. We divided everything in the original formula by 2 to come up with CH2O. The empirical formula does not give us as much information as the chemical formula because we do not know exactly how many carbon, hydrogen, or oxygen atoms are represented by the empirical formula. In fact, there are many compounds that have this same empirical formula. And while we are talking about chemical formulas, a third type of chemical formula is the structural formula, or the Lewis structure. These show the location of all atoms and bonds in a molecule. And here is the Lewis structure for glucose. And this looks a little bit different than the Lewis structures we have drawn so far, because here we do not see the letter C representing carbon atoms. Instead, each vertice is a carbon atom in this Lewis structure. And this is the way Lewis structures are typically drawn for larger molecules. Each vertice is a carbon atom. So I'm going to go ahead and mark my carbon atoms here. I'm going to put dots where there are carbon atoms. There's 1, 2, 3, 4, 5, 6. Those are the 6 carbon atoms in glucose. Also, all the hydrogen is not written here as H. Hydrogen atoms are assumed to complete the valence of carbon. And what that means is that each carbon always has 4 bonds. And if you do not see 4 bonds to a carbon atom, there are actually enough hydrogen there to make 4 bonds. For example, this carbon atom only has 2 bonds. So there are also, and I can draw them in, there are 2 hydrogen atoms also attached to that carbon. But they are not shown in the Lewis structure in order to simplify it. This carbon down here has 4 bonds already, so there are no extra hydrogens attached to it. One of these carbons here, they have 3 bonds to them currently, and so they each only have 1 extra hydrogen attached. Okay, so those are the 3 types of formulas: chemical or molecular formula, empirical formula, and the structural formula, or the Lewis structure. Okay, here this says determining the empirical formula from molecular formulas. So molecular formulas for 3 compounds are given. I would like you to pause the video and determine the empirical formula for each of those. Here are my answers to the problems. Here, the empirical formula for hydrogen peroxide is HO. This is not a compound in and of itself. It's just an empirical formula. And I obtained it by dividing this chemical formula by 2. In the same manner, I divided the chemical formula of butane by 2 to come up with its empirical formula of C2H5. Notice the last one, sucrose, could not be divided by any number to give a different whole number ratio. So here, the chemical formula and the empirical formula are the same because this cannot be further reduced. Okay, now we are ready to talk about finding empirical formulas. And these are very useful because let's say that you are investigating a crime scene and you come across an unknown white powder and you have no idea what it is. The first thing that's done with that powder is that they send it off to a lab, and then the lab gives them percent composition data. And from that percent composition data, the forensic scientists will calculate the empirical formula. This is the first or second step in determining what that compound is. So here, this problem says, a compound was analyzed by using mass spec and found to contain 13.5 grams of calcium, 10.8 grams of oxygen, and 0.675 grams of hydrogen. What is the empirical formula of the compound? There are 3 steps to finding the empirical formula, and we're going to go through each of them here. So first, it says to convert the mass of each element to moles. And we already know how to do that, but the reason we do this is because a chemical formula, whether it's a regular chemical formula or an empirical formula or a structural formula, the formula is a ratio of moles. So I'm going to take the 13.5 grams of calcium and I'm going to convert it to moles. And as a reminder, this is a mole conversion, so you must use dimensional analysis to solve it, and you also must show your work with a number, a unit, and a chemical formula in every position. And looking at the periodic table, I know that for every 1 mole of calcium, there are 40.078 grams of calcium. And when I get out my calculator, I determine that this is 0.337 moles of calcium. I also have to do this for the other 2 elements, and there are 10.8 grams of oxygen. Notice I write just a single atom of oxygen, not O2. That is because this oxygen is not by itself. It is part of a compound, and when it's part of a compound, it is not the diatomic element. And looking at my periodic table, I know that 1 mole of oxygen is equal to 15.999 grams of oxygen, which turns out to be 0.675 moles of oxygen. And the same for hydrogen, 0.675 grams of hydrogen. For every 1 mole of hydrogen, there are 1.008 grams of hydrogen, which means there are 0.670 moles of hydrogen. All right, right now I have mole ratios. I could say calcium 0.337, oxygen 0.675, and hydrogen 0.670. But we do not write chemical formulas with decimal amounts of moles because the chemical formula must also represent atoms, and atoms do not come as partial things. So the chemical formula must also represent atoms and must be whole numbers. Okay, so going on to step 2, this will help us to find out how we get whole numbers from this data. So this says I'm going to divide each mole value by the smallest number of moles. The answer should be close to a whole number. But if any of the answers are not whole numbers, multiply all of the number of moles by the smallest whole number possible that turns your decimals into whole numbers. All right, so first I'm going to look at calcium. And this one you don't generally have to show the work. You can just write 1, but I'm going to show the work here. For 0.337 moles of calcium, I'm going to divide by the smallest amount of these 3. So of these 3, 0.337 is the smallest. And I come up, of course, with 1. What this means is that for every 1 mole of calcium, there is 1 mole of calcium, which is fairly obvious. But now when I get to oxygen, there are 0.675 moles of oxygen for every 0.337 moles of calcium. And this gives me a value of 2. And what this means is for every 2 moles of oxygen, there are 1 mole of calcium. Or I could flip it around and say for every 1 mole of calcium, there are 2 moles of oxygen. I also have to do this for hydrogen. So for hydrogen, 0.670 moles of hydrogen for every 0.337 moles of calcium. Here the number I get is 1.99, and this is not exactly 2, but it is close enough to 2. Okay, so 1.98, 1.99, 2.01, 2.02, those are all really 2. But if you get 1.9, 1.9 is not 2. 2.1 is not 2. Okay, it would have to be much closer to 2 in order to call it 2. All right, and then what this says, and I'm going to say this the other way now, for every 1 mole of calcium, there are 2 moles of hydrogen. And now I have a real chemical formula that has 1 mole of calcium, and for every 1 mole of calcium, there are 2 moles of oxygen and 2 moles of hydrogen. And this answer is perfectly acceptable to your problem, but you might recognize that this is not exactly the way we would write the chemical formula. We would write it as calcium hydroxide. You do not have to be able to do this at this point, but that is something that you might be able to do. But if you can't, don't worry about it. Okay, we have one more example problem, and this one says, what is the empirical formula of a compound that is 25.9% nitrogen and 74.1% oxygen? Here we have the actual percent composition data that came from the lab. And in order to convert this into an empirical formula, when percents are given, assume you have 100 grams of the compound. This means then that if I have 100 grams, I would have 25.9 grams of nitrogen, and I would start with that number. So I would like you to stop the video and do this problem, and then come back and check your answer. Okay, here is my work for the problem. Notice when I did my division by the smallest, I did not come up with a whole number here. 2.5 is not 2, 2.5 is not 3. Therefore, I had to multiply by a small whole number in order to get a whole number ratio. So my chemical formula ends up being N2O5. That concludes these notes. If you have any questions, please let me know. Thanks for listening.